Hi everyone, welcome to the Chem Help ASAP live stream on Wednesday as usual. So there are two things that I want to say before we actually start doing our calculations and start working our problems. The first, as always, and I'm trying to make sure I mention this at the beginning, at the end, is this live stream is for you chemistry students. So I want to know what you want to see. What are you struggling with in class? What do you need help on? If there are problems that you want to see worked. The more feedback you get me, the more I can tailor these live streams to help as many students as I can. So feel free to let me know what you would like to see in any future live stream. The second thing I want to mention is kind of what is on the screen here right now is we are coming up on the AP and also the IB testing season. So I am running a class this year where I will help you review for the AP chemistry exam. So it's going to run in April. It's a 4-week class. We meet twice a week for an hour and a half each. So you're going to get 12 hours of instruction. We're going to work lots of problems. We're going to go over concepts. We'll talk about testing strategies, all that good stuff. If you're interested or you want to know more, I do have the link obviously right here on the screen. I put the link in the description box below, and I think OG Benchmarks is going to get the link in the chat as well. You can also feel free to email me at chemhelpasap.com. Sorry, that's Karen at chemhelpasap.com. And if you've got questions, I will do my best to answer those questions. All right, with those things said, okay, thank you, OG Benchmarks. With those things said, let's jump into some old AP questions and let's work these. So these are going to be questions that are equilibrium-based questions. So obviously the AP exam has a lot of topics that they're going to cover. So this week I am focusing on those questions that are dealing with equilibrium. Now this includes not only just KEQ, but KSP and also KAs and KBs. And hopefully I will get through all the questions so that we can see all of those. But as you know, if you have watched these before, I tend to bite off more than I can chew. So we'll see how far we get. If you do have questions, please feel free to pop them in the chat. I will try to make sure that I keep my eye on what's going on my question screen over there so that I can get to your questions and I can answer them. Okay, with that all being said, let's read our first question. All right, and these tend to be long, obviously, but I'm just going to read through it first. When chlorine gas reacts with ammonia gas, they produce gaseous nitrogen chloride and hydrogen chloride in equilibrium with the reactants. So part A, we're writing a balanced chemical equation depicting this equilibrium. Part B, we're going to write the equilibrium expression. This is a KEQ in terms of concentrations for this chemical equation. Now, just to let you know, yes, they call this a KEQ. You can also call this a KC if you want, because it's in terms of concentrations. Part C, what would happen to the concentration of ammonium upon the addition of more chlorine gas to the mixture? That is at equilibrium. Part D is if the value of KEQ for this reaction is 2.4 times 10 to the negative ninth, are there more products or reactants present at equilibrium? And then finally, part E says, given initial concentrations of chlorine, ammonium, nitrogen chloride, and hydrogen chloride, is this system at equilibrium? If not, in which direction will the reaction shift in order to achieve equilibrium? Explain your answer. All right, so that is a lot to take in. I did give myself lots of blank space. I will have to be switching back and forth because obviously the question is so long that I can't get the question and my work on one page. So there will be some shifting back and forth. All right, so let's go ahead and jump into this question, and we're going to start with part A, and that is write a balanced chemical equation for this equilibrium. Well, they made this just a little bit difficult on us because, of course, they didn't give us any molecular formulas. They gave us names. So this is how, and the IB exam does this too, they kind of bring different concepts together. So you not only need to know what's going on with equilibrium, but you also still have to be able to take a name and write a molecular formula. So let's just get the molecular formulas up, and then we'll balance the chemical equation. Okay, so we have chlorine gas reacting with ammonia gas. All right, so chlorine gas. Chlorine, remember, is one of your diatomics, so it's Cl2. All right, and this is reacting with ammonia gas. Now, ammonia is a common name. But if you have memorized your polyatomic ions and you know ammonium, ammonia is the neutral, the conjugate base of ammonium is NH3. Okay, so those are our reactants. Chlorine gas reacts with ammonia gas. They produce. So that means that I need to have some kind of arrow. I know these are in equilibrium, so I'm going to do equilibrium arrows. All right, so let's get our products in. We have nitrogen trichloride. That's a good molecular or covalent name right there. So nitrogen trichloride, of course, that is a gas. And our final product is hydrogen chloride. Okay, so that again, hydrogen chloride. You could also call that hydrochloric acid, but we tend to refer to this as hydrogen chloride when it's in the gas state. That's just an aside. Okay, so we've got some questions. Sorry, I missed it. Ka and Kb are giving me more. yeah. So Ka and Kb, and they come back. So if you're going to be taking an exam, you've got to be able to work with Ka and Kb. And again, that ties back into Keq and Ksp. These are all Ks. These are all equilibrium constant. No one is confident on the test. So my goal for especially the class is to just give you that little boost of confidence so that when you walk in, you feel like you've prepared as well as you can. And Isaac X, nice to see you. It seems like great. So yeah, no little viewers. So Isaac, it's just more trying to get the word out because I know that this can be helpful to students to work problems and see different things. So spread the word to whomever you know would need this help. Okay, and buffer just wiped. Yeah, we'll do a little bit of buffer. Yes. Well, we have to write the state sub. Oh, point second. Okay, so Isaac, yeah, that's a really good question. So they want to see the states and they want to see your correct subscripts here. So like if you forgot that chlorine was a diatomic gas, then your balancing is going to be different, which means your KEQ is going to be different. Now, the nice thing about the AP exam is they will, so like say you mess up your KEQ, but then you correctly use that wrong KEQ for the next part, they won't take off double points. So you'll only get hit once for maybe getting the wrong KEQ, but you won't get hit again even though your answer for like another part is wrong. So that's the great thing about the free response questions is they will actually grade each piece almost individually. So if you make a mistake in part A, and even though that carries through for the rest, test, then they won't continuously take points off for all the extra pieces. So even if you're not sure about a KEQ, just go ahead and get it down and work with what you've got, knowing that, you know, the graders will have grace on you for that. Okay. Just our Chem teacher said there are multiple times that she will count the, if you forget the ionic charge. Yeah, well, that's, you know, I would guess your teacher just wants to make sure you remember that. But yes. Okay. So I'm going to try to keep eye on the chat there. Yeah, I know that everybody is really hyped up for the AP exam and also the IB exam. They're really very similar. Okay. So let's go back to A. So I'm still trying to get a balanced chemical equation now. So I've got a chemical equation. I have identified my reactants. I've identified my products. I've got my molecular formulas down. But of course, this is not a balanced chemical equation. So let's go ahead and balance that. So let's see. If I go with 3 here, that's going to balance my hydrogens. Now, this is a little bit tricky. When you're balancing your chlorines, remember you've got chlorine in 2 places here. So I have 3 here and 3 here, which means I have 6 chlorine atoms, which means I need a 3 right here. So again, this is the AP exam testing your knowledge of all of these other small things, even though they didn't specifically say, hey, make sure that you've got the right molecular formula here. Okay, so this is part A. This is our answer for part A. This is our balanced chemical equation for this equilibrium expression. And I think I can fit part B in here. So let's go ahead and write a KEQ for this. All right, so remember, whenever you're writing a K, it's products over reactants. So, and again, this is a concentration one, so you notice I'm using the brackets. So we've got our products. Now don't forget that HCl needs to be cubed. So I'm just taking my stoichiometric coefficients, and then those are my powers. And I've got chlorine, that's going to be cubed, and my ammonia here. All right, so that is part A and part B. So even though this goes all the way to part E, at least part A and part B are fairly straightforward. Okay, so part C, actually, I think I'm going to be able to fit this one on here too. Let me make sure. I thought I saw a question. Already finished with content. Yeah, so I know that some classes are ahead, some classes are behind. It's just kind of part of the deal of how different teachers teach and how different classes kind of move through things. Okay, so part C is what would happen to the concentration of ammonium upon the addition of more chlorine gas. Okay, so hold on, I want to underline this. The addition of more chlorine gas, and then we want to find what's going on with, that should be ammonia. Now, I think that was just my typo when I was putting the question in, because we don't have ammonium in this chemical equation. All right, so we are adding more chlorine gas. So if I go back to my balanced chemical equation, I am adding more of a reactant. This goes back to Le Chatelier's principle. So if you add more of either a reactant or a product, the equilibrium is going to shift away from that addition. So if I add chlorine gas, my equilibrium is going to shift away, which means it's going to shift to products. So for part C, I will write this down. I'll squeeze this in over here. If we add more chlorine gas, we are going to shift right, or you could say shift to products. And of course, what would that do to our ammonia, which is also a reactant? That would decrease it. So that would also decrease the concentration of ammonia. Now, again, if you're writing this on the exam, I would use complete sentences. I'm having to kind of pop this into a very small corner here. Go ahead and use complete sentences to make sure you explain your thoughts fully. Again, you want to make sure that you are communicating to whoever is grading your exam. And the better you can communicate, the more points you're going to get. Okay, so that's part C. Now let's go ahead and do part D. So the value of KEQ for this reaction is 2.4 times 10 to the negative ninth. Okay, I do have to go on to the next page. But what I'm going to do is I'm going to just copy down, again, my balanced chemical equation so that I've got this handy. And you'll notice too, so there are a lot of parts to this question, but they're really trying to walk you through all of the steps. So, they ask for what you need first. They ask for that first. Get a balanced chemical equation. Before you can do anything, you've got to have a balanced chemical equation. And then get a KEQ. Before you can do any calculations, you've got to get a KEQ. So make sure that you're using the questions to your advantage. They do put these questions in an order to try and help you work through the problem. Okay, so again, just getting down our KEQ for reference. And this is chlorine and then ammonia. All right. Great. So they told us here, just to go back, that our KEQ is 2.4 times 10 to the negative ninth. So we'll say 2.4 times 10 to the negative ninth. And what they want to know is, are there more products or reactants present at equilibrium? Okay, so think about this. We've got a very small KEQ. We've got a KEQ that is less than 1. So if you have a fraction, or you can think of it as a decimal, then what is going to be larger, your numerator or your denominator? Well, your denominator is going to be larger, or sometimes we'll say the denominator is going to dominate the equilibrium. So what is in the denominator? We've got our concentration of our reactants. So our reactants are going to dominate, which means our equilibrium lies far to the left here. So we'll say denominator dominates. That's like a tongue twister. Equilibrium lies to the left, or we have more reactants than products. Okay. Any question? Yes. Okay. Good. Oh, teaching you Chem. Yeah. Yes. Okay. Great. Okay. So that is, I think that was part D. So let's go ahead and go on to part E here. So here's where we're going to get into a little more calculation. So given initial concentrations, so we have initial concentrations of everything here. We want to know if the system is at equilibrium. Okay, so if you're not sure if the system is at equilibrium, it means you have to run a test, which means you have to calculate Q. And once you know Q, then you can determine if you're at equilibrium, and if you're not, you know which way you're going to shift. So let's write an expression for Q. Now, the great thing is the expression for Q is the same thing as the expression for KEQ, except you put in the concentrations that you're trying to test. This is why we don't call it K again, because we don't know if it's at equilibrium. We're running a test here. All right, one of the key things here, a very common mistake, is putting the wrong concentration in for the wrong species. So again, when you're working this on the AP exam, of course, you won't have to keep flipping back and forth on the page, but just make sure you get all of these concentrations in the correct place, because it's going to make a difference. Some of these are raised to a power, some are in the numerator, some are in the denominator. Okay, so if I'm putting these concentrations in, that is a decimal. And you can sometimes, given these initial concentrations or what you want to test, you can sometimes tell if it's at equilibrium or not just by looking at it, but sometimes you can't. Okay, so this gives me a Q of 0.027. All right, so Q is greater than K, which means I am going to shift to the left, or I am going to increase the concentration of my reactants. Okay, so again, when you're writing this on the AP exam, feel free to use complete sentences. Make sure you explain everything really clearly. I'm being concise here just so that we can keep on moving to the next problem. So this is a calculation of Q. You just compare it to K and you figure out if you're going to shift left or you're going to shift right here. Okay, wouldn't you still use brackets Oh, so are you talking about here where I plugged the numbers in? You totally can. I switched to parentheses just because it helps me see the concentrations a little bit more clearly. But yeah, you can absolutely use brackets. That's not going to be a problem. The brackets just say over here that you're using concentrations, and you're not using pressure. So sometimes if you have a KP, then you're using pressures. You're not using concentrations. But oftentimes when I'm writing any K, I tend to always go to brackets because just that's what we use most often. But yeah, you can absolutely use brackets here, but either way is absolutely fine. Okay. All right, you must be on the strict side. Oh, if you use the parentheses, wow, that is very strict, but it doesn't change your number. And this is while I am not an AP grader, I can't imagine that the AP test would take off for you using parentheses instead of brackets. My guess is your teacher just really wants to hit home that you're using concentrations here, so you don't mix up this one as a concentration and maybe you have moles somewhere else. Okay. So, oh, look, see, I gave myself 2 spaces and I didn't need it. All right, you guys ready for the next question? Again, this is a really long one, as they all are, and this one's got a lot of calculations. So I'm just going to read it through first here. All right, so in communities near the ocean, the overpumping of fresh drinking water from wells drilled into an aquifer, which is an underground reservoir, can lead to saltwater I think this is supposed to be intrusion. So apparently I'm not copying my problems very well. The major cations found in seawater are sodium, potassium, calcium, and magnesium. The major anions are chloride, sulfate, and bromide. Generally, humans can taste salt, NaCl, at concentrations above 250 ppm, which is also milligrams per liter. The Environmental Protection Agency, the EPA, has set this as a recommended standard for the maximum allowable salt concentration. Okay, great. So we've got a lot of information there. So now let's just read through, again, we've got through part E here. So A, they want the molarity of the EPA standard for the 250 ppm solution. B, they're asking for the solubility product of silver chloride. They give a number for this. If 1 drop is approximately 0.05 milliliters of 0.02 molar silver nitrate solution added to a 25 milliliter tap water that has a concentration of chloride that exactly meets the EPA standard, will a precipitate be observed? Okay, so I wish that for this one they had maybe split this up into more than 2 sentences. But what I'm getting here is you have a 25 milliliter sample. You are adding 1 drop of silver nitrate and you want to know if there's a precipitate. Okay, so part C is what concentration of silver nitrate is needed if 1 drop added to a 25 milliliter tap water sample will not give a precipitate if the tap water meets the EPA standard, but will result in a precipitate if the standard is exceeded. Okay, so this is like, again, I wish they had broken this up into more sentences to make this clear, but what they're really asking here is they're asking for what concentration do you need of silver nitrate so you can test a sample of water. So you can add 1 drop of silver nitrate, and if it exceeds the limit, you form a precipitate, and if it doesn't exceed the limit, you won't form a precipitate. So they're looking for that tipping point for part C. Part D, the KSP values for silver iodide and silver bromide are these numbers respectively. When a silver nitrate solution is added to the mixture, that is approximately this concentration in all of these ions. And what sequence will the silver salts precipitate and justify your answer? Okay, so this is a titration. You're taking a solution that has iodide, bromide, and still chloride in here. Here are all the anions, and you want to know which one is going to precipitate first, which one is going to precipitate second, and which one is going to precipitate third. And then finally, our last question is what special precautions should be taken when working with silver nitrate in the lab? So at least we end with a little bit of an easier question and not quite so much math. Okay, so this one is going to be very heavy in the math, but again, we start with part A and we're just going to work forward. And again, they really try to help you out with what they make you calculate in part A, which will help with part B, which will help with part C, et cetera, et cetera, et cetera. Okay, so yeah, you're going to go ahead. Isaac, you're already starting to do the dimensional analysis here. So let's go ahead and do part A. All right, so we've got 250. Now I'm using the milligrams per liters of solution. You'll notice that this was actually really helpful. So they gave you 250 ppm, but they also said this was milligrams per liter, which makes it a lot easier to convert into molarity, I would say, for most students. Okay, so this is just straight up dimensional analysis. So first what I'm going to do is I am going to convert out of milligrams and convert into grams. And then I'm going to convert into moles. Molar mass here is 58.44 grams of NaCl. All right, so what I've done is my milligrams cancel, my grams cancel, and now I've got moles of sodium chloride over liters of solution, so that is molarity. The nice thing is we didn't have to do anything with that liters of solution. It just got to hang out. So if we do this calculation, we're going to get this concentration of NaCl. Again, that is a concentration. This is also our concentration of chloride. So you do want to keep in mind also just generally your stoichiometry and your balanced chemical equations again. So when you put sodium chloride in water, you're going to get sodium ions and chloride ions. These are all in a 1-to-1 ratio, which is why I can say that these concentrations are equal to each other. You do want to be careful with that, because if we had magnesium, or no, not magnesium chloride, if we had magnesium chloride would work, then it'd be MgCl2, and so we wouldn't have this 1-to-1 ratio. We'd have a 1-to-2 ratio. Now, again, I think the AP exam tries to help you in this, and if they can keep something like this 1-to-1, they're going to keep this 1-to-1. Okay. Yeah, select percentage. Yeah. So you just have to watch. This one, they gave you a 1-to-1 ratio, which is great. I mean, that's what we want. It makes things easy, but just be aware when you start setting concentrations equal like that, that you recognize where it's coming from and what the stoichiometric ratios are. Okay, that was part A. So part B, the solubility product. Okay, so we've got the solubility product. We've got a number here. We've got a volume for this one drop. We've got a concentration for the silver nitrate. So this is the concentration of the drop of silver nitrate. We are adding it to this 25 milliliter sample of tap water. Now, there are two ways to do this. I'll start with kind of the longer way, and then I'll show you the shorter way. So, okay, so this was part A. Let's go on to part B. Okay, so we have, let's get our KSP down for silver chloride. All right. Again, you could probably just straight up write KSP down. That's totally fine. I like to, again, have an equation to refer back to. But that just helps me. Again, these are concentrations, so these are brackets, and this is, what did they say, 1.8 times 10 to the negative 10th. Okay, so there is our value for KSP, which means this variable is taken care of. We need concentrations for either the silver or the chloride to solve for something, right? Well, what do we have just right up here? We've got our concentration of chloride already popped in. Okay, so we can actually plug in for our concentration of chloride here, and then we can figure out what's going on with the silver. So I think maybe I didn't want to start with that. All right, so let's go with the silver. So our silver is equal to what is going on, because we know what the KSP is. We want to figure out if it's going to precipitate or not. So let's work with our silver. So if we need a concentration of silver, then we're going to need moles per liter. Again, this is maybe a little bit slower way to go through this, but this is a way that works with the chemical equations, I think, better. So what we did, if I go back to the question, is we added we added 1 drop right here, and they gave us a volume. And we know the concentration of silver nitrate. So we can figure out the number of moles of silver in that 1 drop. And once we know the moles of silver, of course, we can get the volume, which leads us to the concentration. Okay, so here is our concentration of silver nitrate. Now remember, I should put this in green over here. It's still our stoichiometry. So your silver nitrate, this is still a 1-to-1. They're trying to help you out here. That's a 1-to-1 ratio. So my concentration of silver nitrate is equal to my concentration of silver in this 1 drop. So this is why I'm going to go ahead and say that this is my concentration of silver. This is over 1 liter. That just came straight up from my silver nitrate. My 1 drop was 0.05 milliliters. And don't forget your conversion from liters to milliliters. Okay, so this will give us, liters cancel, milliliters cancel. This will give us our moles of silver ions. What is that number? 1 times 10 to the negative 6. This is moles of silver ion in that 1 drop. So we're taking this many moles and we are adding it to our 25 milliliter sample. Wait, why not over AgCl? So yeah, AgCl, that's what we're going to precipitate out. So first I'm trying to figure out what my concentration of silver is. And once that drop has added into the solution, and I'm going to end up comparing it to my KSP value. So this is why I'm trying to get that concentration first of silver in so that I can figure out if it's going to precipitate or not. But yeah, it's because the AgCl is the solid. I know, like, so there's, I feel like this question, there's a lot of silver ions floating around. So like which one does it go to is a little bit tough to keep track of. Okay, so again, if I'm trying to get concentration, I have got my moles of my silver that's in my drop. So my concentration, once that drop is added to my sample, now my sample is 25 milliliters. So my volumes are additive. So my concentration, my molarity is my 1 times 10 to the negative 6 moles of silver. That was in my 1 drop. And this is going to be over my 25 milliliter sample that I added plus the volume of my drop. All right, but don't forget, you've got to divide that by 1,000 because remember, concentration is moles per liter. And we get 3.99 times 10 to the negative 5th. That's molarity. And that is for silver. Okay, so at this point, we've got a concentration for silver. We've got our concentration for chloride. I'm going to plug those into my KSP, and then I am comparing it to my value for KSP to see if it will precipitate out or not. Oh boy, can I fit this in here? I'm going to try. So here is my KSP. Again, it's just my concentration of silver, which I now have. My concentration of chloride, which I calculated in part A. All right, so that is molarity 4.28 times 10 to the negative 3rd. That is also concentration. Oh, where is that calculation? Here it is. 1.7 times 10 to the negative 7th. Okay, so you can see here if I'm comparing, this is my value based on how much silver and chloride I have in solution. This is my KSP. So because my value that I calculated here is greater than KSP, then yes, I will form a precipitate. So because 1.7 times 10 to the negative 7th is greater than my value for KSP, yes, precipitate. Okay, now I did promise that I'd show you a little bit simpler way to do this because you have taken a drop of silver and all you've really done is diluted it. So if you thought of this in the moment, you can actually use your dilution formula to get this concentration of silver. So you can use, I'm just going to put it over here, M1V1 equals M2V2, where your M1 here is your 0.02 molar. That's your concentration. Your V1 is your 0.05 milliliters. That is your volume of your drop. You will solve for M2, and your V2 is your 25.05 milliliters. This 25.05 is your volume sample plus your drop. That's where I get the 0.05 from. So this is a very fast way to get that concentration. I don't know if, you may see that initially, you may not see that initially, but the nice thing is with this problem, you can go either way and you'll still get to the right answer, which is the critical thing. So a lot of these types of problems, especially with the math, you can go two ways. So make sure you're going the way that makes the most sense to you, and don't panic if you do it a different way, as long as you get the right answer. Like, that's what the graders want to see. Okay, so if our concentration here is less than, then you won't get a precipitate. So it won't precipitate out of solution. So that's what you're really trying to find. So if we had, so let's say this number was 1.7 times 10 to the negative 17th. That means the concentration is too low for you to actually get those ions to come together and form a solid. So you're really saying not dissolve, you're saying yes, precipitate, or no, not precipitate out. This actually is a really good question because it ties in exactly with what they want you to do for the next part. So that was part B. Sorry, there just is kind of a block of text here. So for part C, again, I feel like their wording, at least for me, was a little confusing. But for part C, what they want you to do is they want you to create a standard, a silver nitrate standard, where you can take a sample of water, a 25 milliliter sample of water, add 1 drop, and that will tell you if you're over or under the EPA standard. If you're over, you will see a precipitate, and if you're under, then you won't see a precipitate. So that ties into comparing your KSP. Again, they're trying to make you think about that in part B and then apply that again in part C. Because they really are trying to help you, even though I feel like these questions, I just wish they were worded a little bit better, honestly. Okay, but I'm not writing the questions, so we're just going to work them. Okay, so part C. Again, we want to know that tipping point. What is that concentration of silver nitrate? Or you can think of it as just the concentration of silver that you need so that you can do that 1 drop test and go, oh, I see a precipitate, you're over the limit, or nope, I see no precipitate, you're not over the limit. All right, so again, let's just write down our KSP, because this is really kind of what we always go back to, and that value is 1.8 times 10 to the negative 10th. All right, so our chlorine concentration here is still what we calculated, 4.28 times 10 to the negative 3rd. Again, we're trying to kind of dial in that silver concentration from our silver nitrate. Okay, so that means that we want this to equal the KSP. We don't want it to be bigger or less than. We want it to equal this. So I am going to keep this equation here, and I'm just going to plug in my chlorine, and I'm going to see what is that silver concentration I need to be right at that KSP level. Okay, so the math here is actually pretty simple. Again, I am solving for this concentration of silver. That is my tipping point, 8 times 10 to the negative 3rd. Oh, and you see, like, furry therapist, I don't know if you're still watching, but I switched out of brackets. I switched to parentheses. It's just a habit that I have. Okay, so plugging this in, solving for silver. what is that? 4.2 times 10 to the negative 8. So this is the concentration of silver that I need so that I am exactly, you can think of it as being on that razor edge. So I'm exactly on that razor edge so that, again, if you're over the limit, you're going to form a precipitate. And if you're under the limit, you're not going to form a precipitate. Okay, so yeah, you just exactly what you said, Isaac. You're just going to solve for your silver right here. So that is the concentration that I need. Now, your concentration of silver again is your concentration of silver nitrate, because of course, silver nitrate, again, going back to your stoichiometry, it's a nice 1-to-1. So if you know what you want for your concentration of silver, you know what you want for your concentration of silver nitrate. So that is the concentration of silver nitrate that you want, is this 4.2 times 10 to the negative 8th. And that way you can make your testing reagent so that you can just add that 1 drop to it. Okay, I think that was it for part C. Let me go back to part C. Yeah, so concentration of, okay, so they just wanted concentration of silver nitrate there. So again, you're working in an EPA lab. You want to be able to test this thing quickly. You want an idealized or maybe a dialed in reagent that you can just pop, add in, and you can tell immediately if it's over or under the standard. Okay, so that's C. Let's go on to D. All right, so here is where we're comparing our different KSP values. So they give us more KSP values. They give it for silver iodide and silver bromide. Of course, we still have silver chloride right here because we are comparing the chloride, the bromide, and the iodide in solution. So which one is going to precipitate first? And then, of course, justify your answer so we can show a little math here to show how this works. Okay, so this is part D. Now, we can just straight up compare our KSP values. All right, so you know what I should do. So your KSP for silver iodide, let's see, I did write these numbers down. 8.5 times 10 to the negative 17th. For silver bromide, oops, not boride, that was 5.4 times 10 to the negative 13th. And then, of course, our silver chloride is just right up here, 1.8 times 10 to the negative 10th. All right, so you can see that actually I've already written them in order there, right? So the order that they're going to precipitate in is you're going to precipitate out your most insoluble salt first. Or you can think of it as it takes a very, very small amount of silver to precipitate out this silver iodide because the solubility is just so incredibly low. So your order of precipitation is your silver iodide first, your silver bromide second, and your silver chloride third or last, just based on the KSP. Again, we got 10 to the negative 17th, then 10 to the negative 13th, and then 10 to the negative 10th. So I am just straight up looking at the KSP values, and the smaller the KSP values, the more insoluble the salt, which means the less, in this particular case, the less silver you need for a precipitate to form. So yeah, KSP is a measure of the solubility for salts. Exactly. So again, the lower the KSP, the more insoluble the salt. So silver iodide is our least soluble salt in this case. So it is going to precipitate first. It takes just like the smallest little bit, but we can actually show this mathematically. Now this is the same equation over and over again. But if we're going to take iodide, so let's take a look specifically at iodide. All right, so the KSP is silver and our concentration of iodine. And of course, this equals our 8.5 times 10 to the negative 17th. Now the problem, okay, so I got to flip back. the problem did give us concentrations of all of these. So we've got the same concentration of all of these ions in solution, which lets us compare the KSP. So if our concentrations were different, yes, we could look at the KSPs, but we'd also have to look at the concentration. So I'm going to show you this calculation as well. So if I plug in for my concentration of iodide, that's a terrible equal. That looks like a minus. Then I am going to get times 0.00663. Again, that's my concentration. I can solve for this concentration of silver, and that gives me 1.3 times 10 to the negative 14th. Now, what does that mean? Okay, I've solved for a concentration of silver. Like, how does that tie into anything? Well, this is the concentration of silver ions that you need in that sample to precipitate out your silver iodide. So you need next to nothing to precipitate out that silver iodide. I mean, 10 to the negative 14th, that's certainly less than a drop unless you have a super dilute solution. So this is, again, why the silver iodide precipitates so quickly and so easily. But we can do the same calculation. It's the same calculation for our chloride. So our KSP, again, in this case, is just our silver now and our chlorine. And that equals our 5.4 times 10 to the negative 13. So again, I'm just pulling my KSP value there. I am solving for my silver concentration. My chlorine concentration is the same as it was for my iodide. So you can see that my calculation is exactly the same here. It's just I have a different KSP value. So if I solve for the concentration of silver needed to precipitate out, sorry, I took silver bromide there. That's my bad. That should be bromide because I used the KSP for bromide. What is that concentration? This is 8.1 times 10 to the negative 11th molar. So if you can think about the fact that you're taking this sample with the iodide, the bromide, and the chloride, and you are titrating in silver ions. So you're adding dropwise, or maybe you're even splitting a drop here. You're going to first precipitate out the iodide because that is the concentration you need in your sample and nothing else. Then you're going to precipitate out the bromide because you need a little bit more. So this is 10 to the negative 14th. This is 10 to the negative 11th. And just to fit it on the page, sorry, that should be bromide because I used the KSP for bromide. If you also did it for chloride, sorry, I'm trying to just organize myself a little bit here so it can be on the same page. If you did it for chloride, so I won't show the calculation because it's the same calculation. You're just using the different KSP value. The concentration you need of silver to precipitate out silver chloride is 2.7 times 10 to the negative 8th molar. So you need a tiny amount of all of these to precipitate it out, but you need the least silver here for the iodide to precipitate. You need a smidge more for the bromide to precipitate, and then you need a smidge more for the chloride to precipitate. So that is the mathematical justification for the order that we initially put them in, that we just compared the KSP values. But again, the question asked you to justify your answer, and they did give you a concentration of all of your ions, so you can justify it mathematically as well. Okay. All right. So I don't know. We've got one more question in this question, I think. All right. So part E. What special precautions should be taken with working with silver nitrate in lab? Okay, so this is something that the AP exam also loves to do. They like to bring it in and make you think about lab scenarios as well. They like to throw up pictures of like reading burettes and stuff. Okay, so if you're working with silver nitrate in the lab, I don't know if any of you have worked with silver nitrate, but it does stain your skin like a black, brown. It depends on the concentration that you're working with. So if you're working with silver nitrate, you do not want this to get on your skin. So you would want to do things like you'd want to wear gloves. You'd probably want to have long sleeves on and long pants. You would also not want to slosh this around everywhere. So if you are taking a drop, you don't want to be sloppy with how you handle that. You can think of it as, I don't know how many of you cook, but if you're preparing raw chicken, you want to be really careful that none of that raw chicken juice gets in any of your food that is not going to be cooked. So if you have like a dipping sauce, you don't want to put that next to your raw chicken because it might get contaminated. Well, this is the same thing with your silver nitrate. You want to handle it carefully so you don't contaminate yourself by getting it on your skin. But of course, having gloves, long sleeves, and pants are the precautions that you should take, when you're working with it in the lab. Okay, so don't make silver nitrate tattoos on yourself in lab. That's just not a good idea. Okay, so that is that. Wow, 750. Okay, I knew I couldn't get through the whole thing, but that's all right. Let's work through what we can in this third problem. So this is where we're going to work with acids and bases. So we're going to work with Kas and Kbs, and I'm pretty sure I can at least get through part A. This is actually, I think, a really good question. I really like this question because it makes you think a little bit more about your acids and bases. Let's read through it. A student has been given 3 solutions. Solution A is 750 milliliters of a 0.15 molar solution of a weak monoprotic acid. Solution B is 0.05 molar of the sodium salt of the weak acid that has a pH of 9.25. Okay, makes sense. It's going to be a conjugate base. Solution C was made by reacting solution A with 25 milliliters of 0.275 molar potassium hydroxide. Okay, so we've got a lot going on here with these different solutions, and we don't actually have an identity for our acid. We just know that it's a weak acid, and we know that it is monoprotic, meaning it only has 1 proton to donate. Okay, again, they're going to try to walk you through this question with your part A, B, and C. So part A is what is the Ka for this weak acid and the pH of solution A. So you'll notice we have some information on solution A, but we were given a pH of solution B only. So they want to know what is the Ka and what is the pH. Again, pay attention to the order that they ask you to do things. I always like to say there's more information on a test than you realize. They are giving you information. So use the test to help you. So if they've asked for Ka first, and then they've asked for pH, I would try to find Ka first and then go for pH. And that's actually how the order works out. So really use the test, even the questions themselves, to your advantage. So let's try to figure out what's going on with the Ka and getting the Ka for this weak acid. Okay, so we've got 3 solutions that we could potentially use to find the Ka. So which solution do we use? Okay, well, solution A only has the volume and the concentration, so I could get moles of my acid, but that's not a whole lot of help there. I need a little more information. Solution B, I have concentration, which is great. I have the sodium salt, and I also have a pH. So I really like that I have a pH because I have seen other problems where I use pH to then go back in and find some kind of Ka or Kb. So I'm really, attracted to that solution B. Solution C, we've got a reaction going on. So we've got our weak acid reacting with our strong base, which means I'm going to have a stoichiometry problem, and then I'm going to have an equilibrium problem. So I'm thinking that's too complicated. So let's go back to solution B. I think that is going to be our best bet. So that's kind of how I think through which solution to use, which solution is the most likely to give us the correct answer. Are complex acids. So you mean like polyprotic acids, diprotic, triprotic? Yes. Even like I know I won't get to this part C, but you can see we've got a diprotic acid right here. We've got carbonic acid. So yes, you can absolutely see those di, and your triprotic acid would be phosphoric acid. Those are on there. I would say for the calculations, Of the questions, the free response questions that I have gone through, and I've gone through quite a few of them, I tend to see calculations more with the monoprotic acids and a little less with the diprotic acids. But they absolutely can ask you questions about the di and triprotic acids as well. Again, okay, so let's just at least try to get through part A here, because again, I just think this is a really good question. All right, so part A, I want to use solution B. So solution B is the sodium salt of the weak acid. All right, so I'm just going to call this, so usually for weak acids, we call them HA. Again, that's monoprotic. It's got one proton to donate. So I'm going to call the sodium salt of this sodium A. So we don't know what A is, but it turns out we don't have to know what A is. So when I put the sodium salt in water in aqueous solution, of course I get my sodium ions and I get my conjugate base here. So this is my conjugate base of my weak monoprotic acid. The sodium ion is just a spectator ion. I'm going to ignore it. I don't care about it. What I really care about is what's going on with this conjugate base in aqueous solution. Because it is a base, so it has acid-base properties, it's going to establish an equilibrium. So the equilibrium that it establishes is this. So it's in aqueous solution. It's reacting with water a little bit at least. And here we go. All right, so here is our equilibrium of our conjugate base in water. And this makes sense. Again, our pH is above 7, so it is a basic solution. Okay, so I'm going to set up an ice table. Or I don't know if some people call them rice tables, either way. But I'm going to set up my equilibrium here. Now, the great thing is I have my concentration of my acid. So that's 0.05. Of course, these initially are 0. I don't know what my change is, but I know that I'm going to use up some of my conjugate base and form some of my weak acid and some of my hydroxide. So your equilibrium concentrations are just down the column. Okay, I can write a K for this. This is a KB because that's a conjugate base. So I'm calling this a KB because that is a base, but it's still just products over reactants. Now, the nice thing about working with Kas and Kbs is your equilibrium expressions tend to be all 1-to-1, so you don't have to worry about powers, which is nice. Okay, so there is my Kb. I don't know what my Kb is, but I can at least fill in here for my concentrations. I gotta go to another page. All right, I'm just gonna copy this down again. So here is my expression. And again, I'm just plugging in these guys right here. All right, so that's going to give me x squared over, what's that, 0.05? Yeah, 0.05 minus x. And that equals my Kb. Now, at this point, you might be getting a little bit stuck because we have one variable x and we've got another variable Kb. So we've got one equation, we've got two variables where that's a no-go to solve it. So I need some more information. This is why I went for my solution that had my pH, because if I have a pH of 9.25, then I can connect that into my concentration for hydroxide. So first, so pH of 9.25. Recognize that you're going for your concentration of hydroxide. So what I tend to do in this situation is I convert this into, a POH, which of course is just 14 minus 9.25, which equals 4.75. And then I get my concentration of hydroxide. Now you can also take your pH, convert that to a concentration of hydronium, and then take that and calculate your concentration of hydroxide using your 1 times 10 to the negative 14th equals the concentration of hydronium times hydroxide. Either way gives you the same answer. It's just which way makes the most sense to you, and go with the way that makes the most sense to you. Okay, so this is 4.75 equals negative log of our hydroxide. So our hydroxide concentration is 1.78 times 10 to the negative fifth. This is equal to, that 5 is terrible, our value for x. 5. All right, so we have a value for x, which means I can plug in for x in the numerator and denominator. I can calculate my Kb. All right, so Kb is my value of x times 10 to the negative fifth squared, and 0.05 minus 1.78 times 10 to the negative fifth. That's really not going to change it all that much, but that's okay. We can plug it in. We can get a value for Kb. This is 6.34 times 10 to the negative ninth. Now be really careful here, because it didn't ask for Kb, it asked for Ka for your weak acid. Now remember, your equilibrium was started from your conjugate base. So right now, again, you have the Kb for the conjugate base of your weak acid. But because they are conjugate pairs, they are connected by Kw. So Kw, of course, is 1 times 10 to the negative 14th. We will solve for our our Ka using our value of Kb that we just calculated. So here is how we get our value of Ka. Wait. I have that calculation. Here it is. 5.8 times 10 to the negative 6. So there is your value of Ka. And of course, you can go through and then get your pH of solution A. So again, for your pH of solution A, you're going to have to set up another ice table for your weak acid. I just don't have time to go through all that because we're already hitting 8 o'clock. And that is going to be your pH of solution A. So I know we're hitting 8 o'clock, but you guys, again, these live streams are for you. So if you want to see me work through the rest of part A and part B and part C next week, just please let me know. I'm happy to do that. If you want to see other problems or other types of problems, either from the AP exam or from other things, again, the more information you can give me, the better that I can serve you with whatever kinds of problems that you need to do here. Also, just to let you know that if you do want to review for the AP exam, I am running a class in April. I've got a link in the description box. I know there was a link in the chat, and there's a link on the end screen here as well. You can get more information. Of course, please feel free to contact me if you've got any questions or concerns or you just want to know more about it. Anyway, thanks so much for joining me. Spread the word to your friends, and I hope to see you next week. Thanks so much. Bye.
Thank you.